Welcome to my seminar project on the 2014 Nobel Prize in Physics, given to Akasaki, Amano, and Nakamura for the invention of efficient blue light emitting diodes. Akasaki and Amano were working together at Nagoya University after Akasaki had already made his first gallium nitride LED in 1978. His first try, however, was without a p-in junction, which made it very inefficient, and that's why he worked together with Amano on perfecting the crystal growth. In 1986, they both developed high-quality gallium nitride growth on an aluminum nitride buffer layer on a sapphire substrate. 2 years later, they succeeded in having p-type conducting gallium nitride using low-energy electron beam irradiation. And just 1 year later, they made their first p-in junction blue LED. Nakamura, on the other hand, was not your typical academia research physicist. He actually did not have a PhD and had never written a scientific article. Instead, he was working at Nikkei Chemical Industries, developing 2,6 semiconductors. In the same year that Akasaki and Amano developed their first p-in junction LED, he had barely begun his research in gallium nitride. 2 years later, though, he already had developed p-type conducting gallium nitride using a totally different method than Amano and Akasaki, thermal annealing, and he published his first scientific article out. And in that same year, he made p-in junction blue LEDs. Over the next few years, Nikkei Chemical Industries had blue LEDs available commercially with greater than 1 candela brightness, and also created gallium nitride lasers and violet lasers. So it is clear that though Nakamura started his journey in blue light later than Akasaki and Amano, his contributions were still very important, especially this thermal annealing process was much better than electron beam radiation, and helped to make gallium nitride blue LEDs become what we know them today as the mainstream technological advance that we use every day. Before I start this slide, I would like to recommend taking Phi 210, Solid-State Physics by Thomas Grebe next semester, as it is a very helpful class for learning the basics of solid-state physics and what is a semiconductor, what is a superconductor, what are band gaps, what is K-space. All these questions and more would be answered in that lecture. However, for those who did not take the class, I will try to summarize a little bit. So we first have K-space. This is also called reciprocal space or momentum space. And basically instead of x, y, and z coordinates, you will have k or momentum coordinates. It's like a Fourier transform of real space. Now, if you plot energy as a function of k in this K-space, you will get these energy bands. And these black lines that are on this diagram here are the energy bands for gallium nitride. And if you look closely, you will see that between these green and red boxes I've drawn, there are no bands. There are no energy bands in this area, and this is what is known as a band gap. This is a space where electrons cannot have this energy. They cannot occupy this space in reciprocal space, and therefore they must jump in between these two boxes. This red box I would like to call the valence band. This is the energy of electrons when they're in the ground states, and then when they're excited, they can perhaps move up to the conducting band. This is only possible in a semiconductor, well, only likely in a semiconductor. In an insulator, you will have such a large gap between the valence and conducting band that it's very unlikely that you will have electrons jumping up to the conducting band. And this is why you would never use an insulator as an LED material, as you need the electrons to be mobile enough to jump between the valence and conducting bands. Otherwise, you have no spontaneous emission and recombination of electron-hole pairs, and no photon, and no light. In metals, you would also not want to make an LED because metals, the valence band and conducting band overlap, meaning there will be no energy gap, which means there will be no photon emission. This is why semiconductors are always used when making LEDs. And more specifically, we are concerned about gallium nitride and similar materials because we're looking for an energy gap of around 3 electron volts, as this, if you know in the equation E equals hv, this will give us the frequency or wavelength of blue light, which is what we want. So now that you realize that a semiconductor with a band gap of roughly 3 electron volts is what is necessary, some other qualifications we need for our material is that it must be a direct band gap. So a direct band gap will have the minimum of the conduction band and the maximum of the valence band be at the same place in momentum space, which means you can have a direct recombination of an electron-hole pair, and you don't need a phonon. In an indirect band gap, you need a phonon to assist this transition, as the conduction band minimum and the valence band maximum are not at the same place in momentum space, which means you need a delta K, or a change in momentum. And this change in momentum has to be provided by a phonon, which means now you have an electron, a hole, and a phonon, which means you have 3 particles which have to interact. And this interaction is much less likely than just the 2-particle electron-hole pair interaction. And that's why you want a direct band gap, as you want the LED to emit light basically constantly, and not the likelihood of emission to be very low. You want the likelihood of emission to be high. So another characteristic of band gaps is that this delta E of the band gap will not be exactly equal to the energy of emitted photon. The photon will have a slightly lower energy due to the exciton required to excite the state. And this exciton lowers the energy of the conduction band slightly, so you will emit a photon with a slightly lower energy, which is very ideal for a LED, because you do not want this photon to be easily reabsorbed in your material. Because if it's reabsorbed, that means you will never see any light coming from outside, because it just gets absorbed. And if the photon energy is less than the band gap, then it will not be absorbed, or not be absorbed very easily. Whereas if you had a photon with higher energy, or exactly the same energy as the band gap, it would just be absorbed. So this is why direct band gaps are very ideal for an LED. A solar cell, on the other hand, would prefer an indirect band gap, as you want absorption and you don't want spontaneous emission. And that's what you would get for an indirect band gap material. Another important physics aspect of an LED is the p-in junction. P stands for positive and N stands for negative. N-type doped just means it is more negative sample, and p-type means it's a more positive sample. To make this a reality, you just use, for N-type, an atom with a higher valence. Here you would substitute silicon instead of gallium, because it has 4 valence electrons instead of 3. And for p-type, you would substitute magnesium instead of gallium, because it has 2 instead of 3 electrons. The N-type has a Fermi level which is closer to the conduction band, and the p-type has a Fermi level closer to the valence band. The junction between these two, this is just the boundary where these 2 layers collide, and the Fermi level kind of drops in the conduction band of the N-type electrons, and the N-type electrons can then recombine with the p-type holes. And this is very ideal, because in a LED you want spontaneous recombination, and you want the emission of this light, and p-type gives you more holes, N-type gives you more electrons. If you run current through this diode, then you will see that there will always be N-type electrons flowing into the p-type holes, and you will always have this spontaneous emission as long as you apply this current. This is why this makes an ideal LED, and this is why also, even though Akasaki in 1978 had already developed a gallium nitride LED, he spent 10 years, or 11 years actually, trying to make a p-in junction LED, because this is much more efficient than without a p-in junction. So now that I've went over all of the basic physics of what makes a good LED, I would like to touch on how surprising it actually is that it works, an LED, that gallium nitride was chosen. As Nakamura says in his book, Blue Light Diode, all the conferences studying gallium nitride research were almost empty, and there was no interest. And this is because of the lattice mismatch on its substrate, and the crystal growth was just way too difficult. You could not make good crystals. There just was way too many defects. And there was no p-in junction. So he actually chose to look at gallium nitride because his previous research in zinc selenide had always been in competition with other big companies, because he wanted to do something new. And Nikkei was not actually a very big company at the time, and they were actually financially not doing so well and needed to do something new and innovative. So they tried to research into gallium nitride, and well, it worked out for them. But neither zinc selenide or gallium nitride were optimal materials at the beginning. In the beginning, there was no p-in junction for either, and for zinc selenide, there was bad stability, physically and chemically, and for gallium nitride, there was a terrible lattice mismatch, and the crystal growth was not very easy. So in the previous slide, you should notice that the most difficult part of gallium nitride was the crystal growth. You just couldn't get good crystals. They always had major defects, and this prevented it from being a good material for LEDs. So Akasaki and Imano decided to tackle this problem by, instead of using molecular beam epitaxy, they used high-phase vapor epitaxy. And this was a huge improvement, as previously you always had a nitrogen deficiency, whereas they were even able to create a few perfect single crystals. However, the rest of the wafer was still full of defects. But this gave them hope to try other methods to get the same quality on the whole wafer. Using molecular vapor phase epitaxy, they were able to better control the previously way too fast growth rate and allotropic decomposition, and also prevented reverse reactions. With an improved reactor design, they had uniform gas flows and were able to produce gallium nitride homogeneously. This means they had a constant thickness over the whole wafer. But the story doesn't end there. Unfortunately, there were still many cracks and defects. Why are cracks and defects so bad, you might ask? Well, I think I said it before, but I will say it again. You have a photon emitted from the energy gap of gallium nitride. This photon has an energy which is slightly less than the band gap, which means it cannot be absorbed very easily by gallium nitride. However, when you have defects, you will have materials in your sample, you have crystals that sometimes have a band gap that's smaller. And if they have a smaller band gap, that means that they can absorb these photons, which means that the light will be absorbed and not emitted. And we have a light emitting diode, not a light absorbing diode. We want to produce light and not consume it. And that's why these cracks and defects are absolutely catastrophic. And this can also be illustrated in the picture on the right. You can see that in a material with defects, you have the light cones are only emitted on the boundary of the material. And also the reason why there's cones is due to orbital selection rules. The photon is not emitted in all directions, but is a directed beam of light. Now this is actually a nice quality because we like directed beams of light. For example, your flashlight or spotlight will direct the beam of light. So this is actually a nice quality. However, what's not nice is when you have defects and the light is absorbed. So despite all of the progress made in crystal growth methods in the last slide, there were still lots of defects. And the reason for that is the lattice mismatch from the substrate used, which is sapphire, to gallium nitride. There's a 16% lattice mismatch, which is very significant. Even a 1% mismatch would make crystal growth difficult. And here we have 16%, so definitely difficult to grow crystals. And why it's difficult is you can kind of see in the image on the right that the lattice frames will not match up, and because they don't match up with the substrate, defects will form there. And if we didn't have this, if gallium nitride could grow on itself on the same substrate, then we would have perfect crystals in line. The lattice would be the same everywhere in the crystal, and that would be ideal. But that's not available, so instead, Akasaki and Amano developed a really ingenious solution. They used what is known as a low temperature buffer layer. Low temperature is just the buffer layer is grown at a lower temperature than gallium nitride, but what's really relevant is that it makes for the lattice to actually match, because the buffer layer at the substrate matches sapphire, but then at gallium nitride, it's kind of like the lattice in the buffer layer kind of gets larger as it goes to gallium nitride. And this is really genius idea, and due to this, Akasaki was actually able to realize his dream of transparent gallium nitride crystals. And you can see a picture in the middle of this slide is actually how gallium nitride wafers look today. You can actually buy them on AliExpress, should you wish. I found they were too expensive for just this pro-seminar project, so I decided to just attach a photograph. So after high-quality undoped gallium nitride crystals were realized, you would think that we were done. However, for a p-in junction LED, you need p-type and n-type doped gallium nitride. Now, n-type gallium nitride had already been realized. It was hard to control the conductivity, but that is a whole nother problem. Right now, I will talk about p-type gallium nitride, which theorists claimed impossible to manufacture. However, the paper written that talked about that was way before Akasaki and Amano were able to develop the high-quality gallium nitride crystals that I talked about on the previous slide. And so Akasaki and Amano tried anew to dope with zinc, which had been the current p-type doping method for gallium nitride. However, this did not work, so they tried again with magnesium, which had more similar electron activity to gallium nitride. Unfortunately, this also did not work. However, they were close. They then used a genius method called LIBI, and this means low energy electron beam irradiation, and they irradiated the sample, and this activated the magnesium to bond with the nitrogen instead of with the hydrogen, which had been the problem in the past. The problem was that they were using ammonia, NH3, to provide the nitrogen, and then when you try to have magnesium and the NH3, the magnesium bonded with the hydrogen, which was not ideal. The Libby method broke these bonds and gave us the p-type GaN. However, Nakamura had an even more genius method, which was simply thermal annealing, which just means heating up to a very high temperature and then cooling very slowly. He also used nitrogen N2 and not NH3 ammonia, and with this the hydrogen was out of the picture and the MgH bonds were less of a problem. With both undoped and p-type gallium nitride at very high quality using MOVPE growth methods realized, they just needed to make a p-in junction, which is simple as long as you have the p-type doped and the n-type doped. Now the n-type gallium nitride was actually realized a few years earlier. However, it was very difficult to control the conductivity. But once they had the higher quality crystals using the MOVPE growth method, they were also able to overcome this hurdle. And then a p-n junction was made and the first gallium nitride blue LED. On the left, you can see their first LED. And on the right, you can see that the wavelength is not, it's not like a one narrow band. It's a little bit of a wide spectrum. This is actually what separates an LED from a laser. A laser is a totally different method of producing light, but it gives a very narrow band, whereas an LED is a little bit broad. Incandescent light, on the other hand, incandescent light will give you the full spectrum, which is why it's only white, and it's also very, very inefficient, because most of the spectrum the human eye cannot even see, so we're wasting energy by emitting light that you can't see. Speaking of efficiency, this p-in junction LED was also much more efficient than the MIS LED in the past, as you can see from the plot in the middle. On the last slide, you saw the world's very first p-in junction blue LED. At 1 to 1.5% efficiency, it was good for its time, however nothing compared to what we have today. Already 1 year after its invention, in 1993, Nakamura et al. Used different alloys in the molecular orbital vapor phase epitaxy growth method to gain 2.7% efficiency using gallium indium nitride. This is one of the benefits of this growth method, is that you can control the alloy composition. So you can try new things and improve your material. In 1995, huge improvements were made using quantum wells and multiple quantum wells. What you can understand in a quantum well is gallium indium nitride sandwiched between layers of gallium nitride. This means you have your actual p-in junction LED sandwiched between neighboring material, which is different but very, very similar. And this means that your electrons and your gallium indium nitride are confined. They are confined, and this leads to a discretized energy, if you remember your uncertainty principle from quantum mechanics 1. And due to this discretized energy, they were able to get LEDs with 36% external quantum efficiency in 2002. This is actually the value we have today. We have not improved on this very much, unfortunately, but it's also crazy. 36% efficiency compared to 1% efficiency. That's 30 times better. You can't get 30 times better than that, because your maximal efficiency you would get is 100%. But this is also kind of theoretically impossible. But you can never improve 10 times 30%. This will never happen. And this is why this groundbreaking LED that Nakamura was able to work on is really quite fantastic. We can't imagine having something 10 times better. We could maybe imagine having something twice as good, but never something 10 times better. Never in the world. And here's a graph of the LED efficiencies as over time. And you can see when in 1985 they started growing good crystals, that's when they started increasing exponentially the efficiency of LEDs. So perhaps in comparison to other Nobel Prizes in other fields in physics, the applications of LEDs are quite obvious. In household lighting, in light bulbs, in your smartphone screens, basically every light you can think of, perhaps an LED could be suitable for this application. Not for every application, but for most. However, there are other lights that were existent beforehand. For example, the tungsten incandescent bulb. This had about 1 to 2% efficiency. And you might think, well, the p-in junction LED also only had 1 to 2% efficiency. But then we researched and we were able to get 36%. The only problem is with tungsten incandescent bulbs, the theoretical maximum efficiency is only around 8%. So you will never reach the 36% of an LED. This is because they use black body radiation at around 2000 to 4000 Kelvin. As you can see in the picture below, this is kind of the warm white or the soft white or the cool white. And this is just the physical maximum, and regardless of what research is done, it will never be the same as an LED. Now, it is also worth noting that in the future, OLEDs and QLEDs are becoming more and more prevalent in consumer electronics, in TVs, and your smartphone. However, at the moment, OLEDs and QLEDs still have less efficiency than the traditional LED, at least the high efficiency LED in a research lab. Now, your average light bulb that you buy at the supermarket or at the electronics store perhaps only has 20% efficiency, but theoretically there is 36% that couldn't be had, or 40%, yes. With OLEDs, we only had 20%. However, there is more research going, and perhaps we can get 35% efficiency for OLEDs. And it is also worth noting, though, that despite the current focus on OLEDs and QLEDs, which are organic LEDs and quantum dot LEDs, these are not using gallium nitride. There is still research going into gallium nitride LEDs. For example, in this article by Samsung, they are researching into growing gallium nitride onto silicon, and they would use this in their smartphone camera flashes. Now, in the previous slide, I talked about white LEDs, which, perhaps as a side note, white LEDs can be made from blue LEDs by using phosphorus in your environment, and then this will downpropagate the photons to then produce white light instead of blue light. The other application is RGB. To have colorful lights, for example, for stage lighting, which I also personally do in my free time sometimes at the hall, Zurich, you need red, green, and blue. And up until the late 80s, they didn't have an efficient blue LED, but they did have red and green LEDs because these were easier to create because they had a lower band gap due to the wavelengths of red and green being different than blue. Once blue LEDs were also readily available, it was now possible to, as you can see in this CIE color diagram, to make basically every color by combining blue, red, and green. In the following pictures, you will see an 100% blue stage light situation. Now, if I throw in 20% red, then I now get violet. If I throw in 100% red in addition to blue, I get magenta. And if I throw in 100% of red, 100% of green, and 100% of blue, then I get white light. So there are basically two ways to make white light with blue gallium nitride LEDs, either directly or using red, green, and blue LEDs. And depending on your application, either one can make sense. But it is clear that without blue gallium nitride LEDs, we would still be living in darkness, figuratively. Of course, there were incandescent light bulbs. However, the efficiency properties and the fact that you can make white light with them just makes them revolutionary. And that's the end of my presentation. Feel free to ask questions in the comments. And here's my bibliography, page 1 and page 2. Have a nice Easter break.